Hello again. I'm Andrei Popescu, your lecturer for the Software and Hardware Verification module. After the introduction to LTL in the previous videos, now it's time to discuss model checking for this logic. Model checking is a central topic for LTL. The ability to check automatically if a finite system satisfies a property specified as an LTL formula, of course, makes this logic appealing for verification. Here's an overview of what we'll discuss. We'll first define precisely the LTL model checking problem. Then, we'll look at the high-level picture of the model checking algorithm, that is, an algorithm for deciding the model checking problem, which involves 3 steps. These steps revolve around encoding the model checking problem using a special kind of finite automata called generalized non-deterministic Buki automata, GNBAs for short. In a nutshell, for checking that a formula is satisfied by a system, the formula, more precisely its negation, is translated into an automaton. Then a product is being made with an LTS representing the system. An emptiness is checked for the product automaton. The claim will be that this emptiness check is equivalent to the check of satisfaction. So it gives us the answer to the satisfaction question, to the model checking problem. But you will not have to believe this claim. We'll give not only explanations of why this is correct, but also rigorous mathematical proofs. So let's get started. First, let me make an important point about the satisfaction relation. Remember that, given a set of states S, a labeling function L that associates to states sets of atoms, and a formula phi, we know what it means for an infinite sequence of states pi to satisfy phi with respect to labeling L. Written like this. Pi satisfies phi with respect to labeling L. Now, we should note that this does not depend on the exact set of states S and the function L, but only on the labels on states, that is, on the image of L through S. What do I mean by this exactly? I mean that if we have 2 triples, say S, L, pi, and S prime, L prime, and pi prime, of sets of states, labeling function, and infinite sequences of states, then if L gives for pi at each point in time the same labels as L prime gives for pi prime, so in mathematical symbols, L of Si equals L prime of S prime I for all i's, then the satisfaction remains the same for any formula, in that pi satisfies phi, just in case pi prime satisfies phi, with respect to the labelings L and L prime respectively. So in the satisfaction relation, the actual states S0, S1, S2, and so on of the sequence are not important. What matters is the trace of this sequence given by the atom set labeling, namely L of S0, L of S1, L of S2, and so on. We call this trace L of S0, L of S1, L of S2, and so on, the atom set trace of the sequence pi through the labeling L. For example, if L maps S0 to AB, S1 to A, and S2 to B, then the atom set trace of a sequence starting in S0, S2, S1, S2, S0 will be AB, then B, then A, then again B, then again AB. So this corresponds to this, this corresponds to this, this corresponds to this, and so on. We only retain the atom set labels of the states. Since the atom set traces are the ones that determine the satisfaction of a formula, they play a major role in our constructions. As we'll see, atom sets will be the letters of our automata's alphabets, and atom set traces will be the words that this automata can accept. Okay, with these preparations, we are now ready to start our journey into LTL model checking. What is the problem that we want to solve? Remember that LTS stands for Label Transition System. We have an LTS M and a state S0 in it, and an LTL formula phi. The model checking problem for LTL is about determining whether M satisfies phi in state S0. Remember that M satisfying phi in state S0 means that all paths pi of M starting in S0 satisfies phi. By the way, we'll write paths of S0 of M for the set of all paths of M starting in S0. Our main task in the rest of this lecture is to show that there is an algorithmic solution to this problem. This allows us, for each instance of the problem that asks if an LTS is in a state satisfies a formula, to push a button, wait for a while, and then get a yes or no answer to this question. But wait a minute. Why is the existence of an algorithmic solution not obvious? We want to check that an LTS satisfies a formula, and both the LTS and the formula are finite. So why simply applying the definition of satisfaction does not already give us a decision procedure? After all, we looked at some examples, and in all cases we were able to tell whether the LTS satisfies the given formula in a given state. As an exercise, please identify the flaws of this argument.